So, good day students, and welcome to the homework session for the nugget concerning thermochemistry. As you've understood from the theory session, are the thermochemical processes a bit overlapping. If you want to produce a solid biofuel, can the quality be varied by pyrolysis temperature and time? A gaseous biofuel can be produced via pyrolysis or gasification, and a liquid fuel can be produced via liquefaction or pyrolysis. And as you remember from the first nugget in this lesson, is the question of fuel quality central. So how shall you evaluate and judge the process options in a regional context? That is what this homework is about. As with all other homeworks you're doing in this course, is the aim double. You shall learn the theory and you shall learn about your own home region. Or you shall maybe make yourself a calculation tool or familiarize with tools that can help you to evaluate local or regional resources and needs. But in this case, will your task be just a bit more abstract than you might be used to? Looking at this slide, you will certainly feel that you already have a good knowledge of the fundamentals of the three main processes. And you do have an idea of which materials fit which process. And you already know roughly about the overall products. And you have a first idea of how the product quality can be adjusted by tuning the process parameters. But the ultimate aim of this nugget is to make you capable to think critically about thermochemical processes. It might be that you have heard about lots of examples where pyrolysis or torrefaction processes have been successfully integrated in different types of systems. But that does not necessarily mean that a torrefaction process would fit in your own region. So, what I want you to learn is how to think about these things. And for that, you will also have to learn a bit about how conversion processes are evaluated. For that, in turn, you will have to do a bit of reading. As you see from this slide, are the papers you shall read covering different processes and different aspects. But there are certain things on which I will want you to concentrate. You will find the links to all the papers in the link list with this nugget. The papers listed represent 140 pages in all, but I will try to explain what you shall look for in the specific papers, and you shall not read all the pages. There are two major measures that are used to describe the overall efficiency of conversion processes, and they are the energy efficiency and the carbon conversion ratio. You must remember that the aim of any conversion process is to conserve the energy and just transfer it from the feedstock to a new substance. A conversion process is not to make use of the energy. It's only a transfer process. So the energy efficiency is a measure of how well you succeeded in keeping the energy. So that is a measure of the thermodynamic efficiency in the process. The other measure is to quantify how well the process succeeds in conserving the elements. You can set up a mass balance for any of the elements, but the most common measure is to just compute how much carbon is retained from the feed to the product. The ultimate aim of this nugget is to make you capable to think critically about thermochemical conversion processes. And to do that, you will have to be able to think in terms of process efficiency. You will understand that to evaluate the energy efficiency, you must be well familiar with heating values and the energy content in different feedstocks and products. And you will understand that to do a mass balance for carbon, you must be well familiar with basic chemistry, stoichiometry, and you must also have an idea of how the composition of a product mix might look. Just for example, suppose an anaerobic digester produces a gas which is 50-50 carbon dioxide and methane. If there would be no carbon in the digestate, you would see that the carbon conversion for biomethane would be 50%. So the reading you shall do is to make you build some of the most fundamental understanding of these things. A bit of thermodynamics and a bit of product composition. This paper is only 8 pages, so scan through it. It refers laboratory experiments, so the results may not be completely transferable to full-scale processes. But what is presented are chemical analysis of 6 different feedstocks and the heating values. And then you will see product gas data from 2 different pyrolysis processes. Use these data to try to figure out how to evaluate the carbon conversion. To do that, you will use the universal gas law, and you will use some basic chemistry. And then have a look at the energy efficiency. Do you have all the data needed to do the evaluation? Is anything amiss? If so, can you do a smart approximation? This paper is 30 pages. What you want to read are the process descriptions in section 2, starting on page 3, and in section 3, all until section 323 on page 16. The thing with this paper is that it describes in short indirect liquefaction, liquefaction through hydrolysis and fermentation, liquefaction through pyrolysis, and hydrothermal liquefaction. So in less than 15 pages you get a short presentation of 4 different processes, including short characterizations of the processes. And then you should also pay attention to the bio-oil analysis shown in table 6. This paper is 30 pages, and it is a review article, so it reports and summarizes findings from literature. Section 2, total 11 pages from 2942 to 2953, will give you an overview of gasification techniques and reactor types. Section 3, which is 3 pages, will give you an idea of suitable feedstocks and potential products. Section 4 extends to page 2959 and again treats the influence of operating conditions on the product and on the process. So concentrate on the 17 pages, ranging from 2942 until 2959, and then read the socioeconomic analysis on pages 2967 and 68. The sections about tar, electricity production method, and mathematical modeling are of no interest to you right now. In this paper, have the authors actually done some laboratory experiments using different biomasses, different reactors, and different sets of operating parameters. The most interesting part of the paper, for your understanding, is section 3, pages 5 to 10, where the results are presented. When you read this section of the paper, then again try to get a feeling for the influence of raw material and process parameters on the product. And then read section 3.5, starting on page 10 and running until page 12. When you read this section, you shall ask yourself if all the numbers presented will be sufficient for you as a reader to evaluate the energy efficiency of the process setups. Would you need any more information to be able to do an estimate? And in that case, which information? This report is 77 pages, but what you shall read is chapters 4 and 6. Chapter 4 deals with efficiencies, and you will see several examples of real case efficiencies. This will help you to keep your head cold and clear when you meet folks who want to sell you a gasifier and tell you the most fantastic numbers about efficiencies. So the idea with chapter 4 is to make you get a realistic view of gasification as a process. Chapter 6 lists a number of installations and gives some data. What you shall actually do in this homework is to judge if a thermochemical conversion route is feasible in your region. So together with chapter 4 will this chapter put your feet firmly on the ground and hinder you from dreaming. When you read about the different projects, you will have to think about the specific conditions for the individual projects in their regions. Try to figure out what role the specific conditions had for the specific project solutions. How do you think such local conditions affected the project plans? And how would you apply that to a project in your own region? Now it's time to concretize your task. What you shall do is to identify one regional biomass that would be suitable for a thermochemical conversion. Remember that data for lots of biomasses are available in Phyllis, so you will most probably be able to find the raw material, ultimate analysis and heating value. And then select one customer who could use the fuel. So then you have identified the endpoints of the energy supply chain. Now quantify the amount of energy that the customer requires, and then try to make an assumption concerning the possible output from the conversion plant. Then apply a realistic energy efficiency to compute the necessary energy input to the conversion process. And then finally use the heating value of the selected biomass to estimate the total amount of biomass you have to harvest and transport. And also check the carbon conversion rate. You know what the customer needs. You will have estimated the losses from the conversion plant to the customer, so you know the necessary output from the conversion plant, and then applying the conversion efficiency or the energy efficiency, you will be able to estimate the necessary input. Do you think a conversion plant might be feasible in this application in your region? After all, you have read about some practical examples and experiences, or you may have to try to find information on the web. Write down your observations in a promemorium for yourself. You will have good use of that later in this course. Remember that the quality of your notes shall be academic master level, and that holds true even if your writing is only for yourself, like in this case. As a help to do the calculations, I would suggest you download the PowerPoint slides from Thomas Nordgren at the Royal Institute of Technology in Stockholm. There will be no need of further explanations to these slides. They are self-explanatory.